on this computer, and hopefully this is recording. Okay. Okay, and let me make sure. All right, let's start with prayer. Father God, we thank you again for another opportunity to study mathematics. And as we learn how you use science, you use mathematics for your creation, and how this universe so wonderfully, so beautifully represent your knowledge in mathematical forms. Help us to be diligent in the study of this course and any other classes that we are taking, so that we can be workers that brings glory and honor to your name in different ministries that we all do. We commit this session this week into your hand, and I pray your blessing upon all the students for this class and also other classes that they are taking. I ask your blessing in their ministries that they do for your glory. Pray these things in the Lord Jesus' mighty name. Amen. All right. Any question?
Not for now.
Not for now. Okay. All right.
I don't remember it. Go on.
Okay. Let's go on. We are going in this class going to talk about sets, subsets, different kind of sets, because these are the basic block, the fundamental blocks of mathematics and vocabulary of mathematics. Mathematics is like a language, and any language has its own vocabulary. So we are learning these different vocabulary and these building blocks to be able to speak and understand mathematically. We're going to talk about set. What is a set? Is a collection of objects which are called elements or members of the set, as you can see in the PowerPoint. Let me go back to the previous slide. Like, for example, set number 1 is a set of dinosaurs. Set number 2 is a set of different butterflies. Set number 3, different kinds of vehicles. So it's a collection of objects, and those objects are called elements or members of the set. A set is well defined if its contents or its member can be clearly determined, can be clearly identified. There are 3 methods commonly used to indicate a set. We describe them like, we had on the previous slide, a set of dinosaurs, butterfly. We use a roster form. I will explain what that is later, or through set builder notation. Now, let's start with description of set. For example, when someone asks you write a description of a set containing elements of Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, basically the set is the days of the week. That's all there is to it. That's a set, days of the week. When we want to list elements inside a set, we use braces, as you can see on the PowerPoint. I am concerned whether this is... Sure.
It's a PowerPoint slide.
Yeah.
The other one.
Oh.
It's to the,
No, it's this one.
the other one. The one that's left or right. Yeah.
This
Right,
one?
left. Yes. That's
Okay. All right. Hope that. All right. Hopefully, I don't know. I hope it's working. In any way, you have the PowerPoint, and I will make sure when I use the whiteboard, I will stop the share, and because I notice you can see it larger if I only record from the board instead of shared. When we want to list elements inside a set, we use the symbol braces. And then this is called roster form, where the elements are separated by a comma. For example, when you have, two braces, and as you can see in your PowerPoint, 1, 2, 3, this is a roster form notation for the set whose elements are 1, 2, 3. But if we use parentheses or if we use brackets, no, those do not indicate a set. It must be braces. Set is generally named with a capital letter. For example, the name commonly selected for the set of natural number or counting number is N, capital N. Okay? Like natural number. Here you see capital N, then 1, 2, 3, 4, 5, and then you have those 3 dots. Those 3 dots are called ellipses, indicating the element in this set continue in the same manner, 6, 7, 8, 9, till infinity. Now, the roster form of the set, which, for example, here, let me do all of that. If we want to express the following set, these are descriptive. We want to express them in a roster form. Number 1 says set A is a set of natural numbers less than 5. So as you can see here, the natural number less than 5s are 1, 2, 3, and 4, but not 5 because it says less than 5. So we write that capital A, then equal 2 braces, 1, 2, 3, 4 with a comma. Okay. It says set B is a set of natural number less than or equal to 75. But you don't need to write all the numbers. You again, B equal 2 braces, 1, 2, 3, 4, comma, then we put the 3 ellipses, 3 dots, all the way including 75, because this time says less than or equal to 75. Set P is a set of planets in the Earth solar system. So P, then braces, the name of the planet starting closest to the Sun, Mercury, Venus, Earth, all the way to Neptune. We used to have Pluto, but the astronomers subtract that because they said it's a dwarf planet. Anyway, I think it's a planet. Yeah. Now, we use inclusive. When we use inclusive for the sets, for example, it's the set of natural number between 4 and 9. Okay, between 4 and 9. It means 4 and 9 are not included. So we have set A, 5, 6, 7, 8. These are between 4 and 9. If we say the set of natural number between 4 and 9 inclusive, meaning 5, 6, 7, 8, but the numbers 4 and 9 are also included in the set. Following? You see the difference between these two? The first one says only between 4 and 9. So it's 5, 6, 7, and 8. The second one says between 4 and 9, but inclusive. Meaning include those two ending numbers. Include 4 and 9. All right?
All right, thank you.
Any part, anything is not clear, please ask, okay? Because I tell you one thing, when I studied mathematics in college, one reason that I studied mathematics, and I was able to be double major, I studied mathematics and physics together, was the reason was this, that I realized if I understood this concept, the subject, I had to do very little work. The work was easy, provided that you understand the principle. You understand the principle, the rest is very easy. It has, you know, some people are very good with mass memorization, and they, you know, they do good in biological sciences. I'm not good with that. So I loved mathematics, physics also, because provided that I understood this, the principle, the rest was easy. I didn't need to do mass memorization. You have to memorize some things in all fields, but in mathematics, provided that you understand the building block, then the rest are easy. So we talked about set can be described in descriptive, roster form, set, or set builder notation. When we talked about set builder or set generator notation, we use a symbol that is frequently used in algebra, the symbol that looks like a strange looking E. And that E means this is an element of, it indicates membership. For example, you have here a set A, 5, 6, 7, 8. We can say 6, the number 6 is a member, is an element of this set, because it's right there. But number 9 is not an element, is not a member of set. All right? These are simple, but it's important to keep them in mind. These are vocabulary of mathematical language. Okay? So if you look at the set builder notation here in the PowerPoint, again, we have the two braces. Then you have in the middle that perpendicular short line. And it says all x such that all x less than or equal to 2. So this set includes all the number in such a way that are less than or equal to 2. Okay? So it can include 1, 0, and if there are no restriction, we can go into negative also. Now, if you look at your textbook, but I have it also here, table 2.2, for example, it says x less than a. So set builder notation would be all x such that x is a natural number but less than 4. Now, when we talk about natural number, it cannot go negative. Okay, so it would be numbers 1, 2, and 3. Now, look at the next one. It said all x less than a, but x is a natural number and it's less than, and now here we said a is 4. All x that are less than or equal to 4. So now we are including 4. So it would be 1, 2, 3, and 4. All right, sit. Look at the third one. X greater than a. And x is a natural number. So all natural number greater than a starts with 5, goes all the way to infinity. Look at the next one, the fourth one. X is greater than or less than a. All natural number greater than or equal to 4. So it includes 4. Now, the other one is interesting. It would be 1, 2, 3, 4, 5. The fifth one. All numbers between a and b. Then, here we are setting the boundaries. The set builder notation is all x, where x is a natural number and it's greater than 4, less than 8. Greater than 4, it goes 5, 6, 7, but it has to be less than 8, so it cannot go more than 7. Right. If you put equal sign, it will include 4 and 8. All right? Or you can do equal sign only for one part or the other part. Is that clear? Okay. Cardinal number of a set. Now, what do we mean? A set has a cardinal number. It's represented by n of a, or little n, in parentheses a, is a number of element, distinct element in a set A. For example, the symbol n, then parentheses a, is read n of a. The cardinal number tells us to answer the question how many. For example, let's look at page 50, example A. Let me put my textbook. Okay, page 50, example 8. All right, no, I better stop share. Okay, yeah, I'm still recording. Yeah, because I want to. Okay. Now, find the cardinal number for each of the following set. Here on page 50, example 8. Here we have a set A. So we have capital A, braces. Could you tell me the numbers?
Yes. It's 7, 9, 11, and 13.
Okay, what's the cardinal number for this?
4.
Yes, that's right. 4 distinct elements. So n of A is equal to 4. Okay. Let's look at number B. We have set B is equal to 0. Yeah.
Yes.
So what's the cardinal number for this?
1.
Yeah. And B. Look at C. Set C. It says starts with 13, 14, 15. Then 3 dots and goes to 20, 23. Now, what does these 3 dots mean?
That goes all the way to 3.
Yeah, it continues.
Continue.
Yeah, it continues between 15 and 22, which include numbers 16, 17, 18, 19, 20, and 21. It means the inclusive. So, what's the cardinal number for this set? 12. Let me see. 11. Yeah, because it starts with 13 and goes to 23. The way I do it in my mind,
Yes.
take 23 and subtract 12. Go one less.
Yeah.
Gives you what's in the middle.
Okay.
So the cardinal number for this would be n of C is 4. Let's look at
That's
Sure. Let's look at number D. So that sign, this sign is a sign of empty.
Mm-hmm.
So it's an empty set.
Exactly.
So what is its cardinal number?
Zero.
Zero. Empty. There is no member in it. So the cardinal number of D is zero. Okay.
Mm-hmm.
All right.
Oh, but interesting to see that in letter B equals 1, although it's 0.
Zero is a number.
Huh.
Zero is a very important number. Zero plays a major role in mathematics, and one of the advantages of our mathematical system, Arabic Hindu system, is we have zero. Those numeral systems that you studied, their disadvantage was lack of zero. But you know, in Arabic numeral, you can make all the numbers from 0 to 9. Only with this 10 digits, including 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you get you can build all the numbers you want. But remember the Roman numeral, the Hebrew numeral, all those others numeral, they don't have zero, and they are not positional, so they had to have these huge numbers. And that's one of the reasons that those cultures, those societies did not survive and did not advance. Okay. All right. Let me go back to share again. I hope this is recording with share. Okay. Finite and infinite sets. A set A is a finite set where A is an empty set, or N of A is a natural, not an empty set, N of A is equal to 0, or N of A is a natural number. Then it means either 0 or all the natural number. The natural number starts from 1, goes all the way to infinity. So it's a finite set when A is empty set, or N of A is a natural number. A set whose cardinal number is not 0 or a natural number is called an infinite set. For example, we have here set N, capital N, 1, 2, 3, 4, 5, 6, and then 3 dots. What is it, finite or infinite? Of course, I've written it, but look at it. What do you call that set? Is it an empty set? No.
No, because
is it? So it's not as. It has to be if N of A is 0, or N of A is a natural number. But N of A here is infinite. It continues to infinity. Therefore, this is an infinite set. A finite set, for example, would be if I had N equal races 1, 2, 3. This is a finite set. Okay. I only have 3 elements. Or if N was empty, my cardinal number is 0. Right. But when there is no end to the set, it will be infinite set. Okay? Mm-hmm. Clear? All right. Universal set is all the elements or member of any group under consideration. Universal set would be, for example, all the students at Southern California Seminary. That would be a universal set in that definition. It has subsets, students in undergraduate, master degrees, doctoral degrees, student in biblical studies, student in psychology. Those are subset of that universal set. The universal set will include all of them. Okay. The cardinal number is finite and signed as aleph null. Aleph, the first letter of Hebrew alphabet. Clear?
Okay.
Okay. The cardinal number for universal set. Okay. The cardinal number of the universal set is infinite because it includes everything. All right. Now, equality of sets. Set A is equal to set B. That means that both of them have exactly the same element regardless of their order or even possible repetition of the elements. We write set A equal to set B when we want to write it mathematically. For example, look at the PowerPoint. Set A has WXYZ, set B has ZYWX. They are equal because they contain the same element, even though the order of representation are different. Let's look at example 10, page 53. It says, find out whether each statement is true or false. Number one, it says set A 489 is it equal to 894? Yes, that's the same element. B 135. Actually, I just look at it. Is it equal to the other one? No, because the other one has 0. Okay, so that was B. Let's continue. Now we come to subset. Sets have subsets. Set A is a subset of set B, and that's how we write it, as you can see in the symbol in the PowerPoint. A is a subset of B. When only all the elements of set A are also elements of set B. Set A is not a subset of set B and is symbolized by A, crossing that line, not B, when it doesn't, its element is not also part of the other set. Okay. Let's look at example 1, page 57. All right. Now I tell you again, stop. Example 1, page 57. You have set A 1, 3, and 1, 3, 5, 7. Set B 1, 3, 5, 7, 9, and 11 is a subset of. Yes, because all the elements of set A are included in set B. Okay. So the set B is bigger than set A. It has to. It has all the elements of set A. It has 1, 3, 5, 7, and it has 9 and 11. They are not equal, but set A is a subset of set A. Now, look at the next one. It says set A, where set A X is a letter in the word proof. Okay? So it can be the letter P, it can be the letter R, or it can be the letter O, it can be the letter F. Okay?
Yes.
Set B, all the letters Y in the word roof. So it can be R, O, F. Is this one is set A a subset of set B?
No.
Why?
Because it doesn't have P.
That's right. Now let's look at number C. X is a planet of Earth's solar system, and is A subset of B?
Yes.
Yeah, all the planets are there. So just look at you compare both sets, and you just want to make sure all the elements in set A are in set B.
Okay. Right. And that's a subset.
Yeah. So A becomes subset of B. When it's not, we write it the other way. We say A is not subset of B. All right. Okay, this is recording. Good. Get void. Now let's go again to shared. Okay. Proper subset. Okay. If A is a subset of, but not equal to B, A is a subset of B, but it's not identical, it's not equal to B, then we call it a proper subset. It says look at page 58 regarding proper subsets. If you look at proper subset, for example, on page 58, at the bottom of the page, you have 1 and 3 are proper subset of set B, 1, 3, and 5, because all the elements are there. You see, all the elements are there, and they are not equal. They are not identical sets. So set A is a proper subset of set B. But look at the other example, at the very end. You have set A 1, 3, and 5, and then set B 1, 3, and 5. They are identical, but you cannot call it a proper subset because they are identical.
Yes.
So we use the other sign to identify it's not a proper subset. Okay, review example 2, page 59. All right. Okay, I have to stop sharing. Page 59. Right. If it's it's an improper subset or a proper subset for each of these lifetimes. Okay, for example, number 1. X is a person, all the person, and X lives in San Francisco. Okay? Set B, X is a person and X lives in California. Is this a proper subset or improper subset? Yeah. All the elements of set B are included in set A are included in set B, but they are not identical because there are people who live in California, but they don't live in San Francisco. So you can say, it's every person living in San Francisco is also a person living in California. Each person in set A is contained in set B, as you can see by that notation, but they are not identical, therefore it's a proper subset. A is a proper subset of. Now, the example number B, you have 2, 4, 6, 8. B is 2, 8, 4, 6. They're identical.
Yep.
So they are equal. Therefore, it cannot be a proper subset. All right.
Is it called improper or just
Improper. Proper subset. Actually, identical. You know, it can be, yeah, identical. I can call it improper subset. Look at that checkpoint number 2. It says set A is 2, 4, 6, 8. Actually, well, actually 2, 4, 6, 8. The set B is 2, 8, 4, 6, 10. Is A a subset or a proper subset of B or not?
A is a proper subset?
That's right. How about B? X is a person and X lives in Atlanta. B is X is a person and X lives in Georgia.
It will be a proper as well.
Yeah, because all the people who live in Atlanta, they also live in Georgia, but they are not equal. But Georgia and other in other cities. All right. Okay. All right. Let's continue. Empty set as a subset. The empty set is a subset of every set and is symbolized by, you know, that null sign. Furthermore, empty set is a proper subset of every set except itself. All sets, nothing can be part of all sets. And nothing can be also proper subset of all set except for itself. So we write set B. For any set B, any, whatever, the null, the null sign is a proper, it's both part of any other set and it's also a subset of any other set. You see that? See the first one, number 3, says empty set can be a subset of every set, and number 4 tells us it can also be proper subset for any set B other than the empty set. Empty set is a subset. All right. Now, I think when we come to diagrams and visualization, it helps. Here you have a picture, okay? A rectangular picture, a circle in the middle. The circle area is called A. Whatever is not in A is called A prime, not A. A would be the universal set. Whatever is not in A is A prime. Both of them together form the universal set. If our universal set are all the students in Southern California seminary, then if A is a set of all the undergraduate students, then A prime is a set of all the others in other programs. But both of them together form the universal set for Southern California seminary. All right. Now here, these are much more easier to comprehend. It makes it easy. One, you see all that discussion about set, member of a set, proper subset, it comes handy here, and it will become handy in ministry. For example, if you are doing some kind of research, some kind of analysis of your church, you want to find out how many teenagers are participating in prayer, participating in the Bible study meetings. How many teenagers from the different families come to church? They don't come to church. They use these kind of diagrams to find out. It visualizes the situation for you. Intersections, for example, here we have 3 circles A, B, and C. A is the red one, B green one, C is the blue one. You have their intersections, for example, between A and B in that yellow one. What it means is those elements that are in that intersection are part of both set A and set B. The white one is an intersection of A, B, and C. All the members that are there in that white area means they are elements of set A, elements of set B, and elements of set C. It would be, for example, if you're doing a research study on the condition of your church, you will, for example, that white area would be a member who participate in all the meetings. A and B would be a member who comes only for Sunday, or maybe one of the meeting during the week. Same A and C, you see, intersection of A and C. Or B and C would be a person who comes to 2 meetings during the week but doesn't come to Sunday. Okay? If it's defined set as those who come to Sunday morning service. Okay? Now, the union of set and B is symbolized by A, that sign which looks like a U, UB, is a set containing all the elements in both of them. Set A and B. This is called the union operation. For example, in our previous picture, the union would be all the people who come to any of the meetings. Okay?
Yeah. So the intersection is symbolized by like kind of an and. Kind of.
Yeah. The upside down U.
The upside down.
Okay. All right. Now we have here a diagram called Venn diagram. We have again set A, set B, set C, red, yellow, and green. Then you have all these subsets and all these intersections. For example, you have set A includes the small a area, D, G, and E. Set B includes B and F and G and D. C includes C, small c, E, G, and F. Okay, the outside would be none, would be an empty set. You know, you see that, the none? So nothing outside. All right, for example, we have 2 sets, and they are properly defined. One is soccer set, one is a tennis set. They have their clear members. The union of these two is people who play one of them, either soccer or tennis. So it would be Alex, Casey, Drew, Hunter, and Jade. The intersection is only Casey and Drew, means these 2 guys play both soccer and tennis. Following me?
Yes.
Okay.
Yes.
All right. Now, intersection is Casey and Drew. So here in the next diagram, you can see it better. All right. The difference, if we want to find people who only play soccer, soccer minus tennis would be Alex and Hunter. So if the U is a union, that reverse U, N, like N is intersection, must be in both, and that minus sign is difference. In one set, but not the other. Let's say, for example, there is a 3rd set, volleyball. There is Drew, Glenn, and Jade. So volleyball has these 3 guys. S is for the soccer, T is for tennis, and V is for volleyball. Okay, so the union of them would look like that picture that you can see on your PowerPoint. It includes all of them. Drew plays soccer, tennis, and volleyball. But when you look at their intersection, you find only one of them that plays all the three. So that, for example, here we are using it for sport, but it can be used for ministry. You can find out which are the members, who are the members that participate in all the meetings. Okay. Jade plays tennis and volleyball. Okay. Alex and Hunter, they play soccer, but then they don't play any other game. And we don't have anybody who plays only tennis. Look, the intersection of we, no, I'm sorry, the intersection of T with the other two, with soccer and volleyball, minus, you know, this area, that area of a T, that meaning if there was somebody there, it meant that this person only plays tennis. We don't have anybody who only plays tennis. Okay, is that clear? Yes. Now, let's look at set C. Set C is Alex, Casey, Drew, and Hunter. There are four members that they play soccer, but Casey also play tennis. Drew also play tennis. Okay, those two. The union of set T and V, those who played both tennis and volleyball, would be Casey, Drew, Jade, and Glenn. The intersection of set S and set V has only one member, Drew. There's only one person who plays both soccer and volleyball, right? What is it? The empty set. This is the intersection of set S and set V minus set T. We want to find intersection of S and V without, we don't want any interference from set T, nobody. There's no member. That's empty, empty subset. Okay. The universal set will include all these guys, including Blair and Erin and Francis and Ira, who don't play any of these three games. Okay. Everyone who does not play soccer, so we have the soccer there as Alex and Hunter, Casey and Drew, who we want a set that people who don't play soccer. So we take the universal set minus the soccer set, we get those guys. Blair, Erin, Francis, Glenn, Ira, and Jade. Okay. It's the purple part. Okay. Complement everything that is not S. So here's a set S. Everything that is not S is S prime, is that purple part. But S and S prime forms the universal set. Let's look at example 3, page 68. Okay. Look at example 3. You have U, set U is 1, 2, 3, 4, 5, 6, 7, 9. Set A is 1, 3, 4, and 7. Find what is A naught. What is A prime? All the members who are not in A. What are the numbers who are not in A? So you go to U. U is a universal set. Just cross 1, 3, 4, and 7, as you can see with text. Okay. All right. So A prime or A naught has 2, 5, 6, 8, and 9. Which should be also the picture there, figure 2.12 and figure 2.12. Why are set important? You know, as I mentioned, they are vocabulary of mathematics. They allow us to treat collection of mathematical object, in fact, collection of object as mathematical principles. They are a starting point to any mathematical definition. And without them, we would be hard-pressed to define mathematical operation. We will talk about functions later, but for example, here, a function is a rule that maps numbers to other numbers. But again, what's a rule? That seems quite vague at this time. You will understand it later in other chapters. For example, 2x, is this the same? The rule, is this the same as 2x plus 1 minus 1? Well, they are different rules in both of them, even though they yield the same output. Because plus 1 minus 1 cancels out. But there are different rules. Hence, we define a function as a set of ordered pairs. I will talk about them more clearly as we go further in our textbook. In chapter 6, we will talk about domains of function. A function maps numbers to numbers, but the same concept of rules that maps things to things pops up all over. Operators maps functions to numbers. Now, don't worry about all these things might be confusing. We will come to them in later chapters with example. Okay, just remember, function maps numbers to numbers, operators maps functions to numbers. Operation in a group map abstract group element to each other elements. Other strange function might map equivalence cases of infinite sequences to infinite sets of rational number and so on. But here you can't precisely pin down what things means unless you have mathematical notation. Okay, definition that we use in mathematics that relies on sets, algebra heavily, topological space heavily use sets for their operation. The whole modern algebra is that we can apply a set of anything as long as the operation obey the rules. Okay, so don't worry about those. No, it can be confusing at this time, but just please read them and remember, you know, what we are talking about. These whole concepts of sets will come handy when you talk about functions, when you talk about operations, when you talk about algebra and topology. Number representation and calculation, this comes to that subject of different numerical system. I have all those videos for you on lesson 2. Please watch them carefully. We use Arabic numerical system, Roman, Greek, Egyptian, all those Babylonian, Chinese, you know, Mayan. They failed because of their lack of ability to handle mathematical operation. Okay, system of numeration. Basically, when we talk about system of numeration, we are talking about sets of basic numerals and rules, combining them to represent numbers. You know, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the numbers, the basic digit that we use, and we have rules. 1 plus 2 is 3, 3 plus 5 is 8. That's our system of numeration. But we also have place value. That's very important. Or positional value. That tells us the value of symbol depends on its position in a number. For example, the digit number 2, the number 2 in 20 represents 2 tens. But the same number, the same digit 2 in the number 200 represent 2 hundreds. But you see that easiness, the flexibility of our system is we don't need to come with different number or different digit to represent 200. We change the position of 2. All those numbers, the basic number from 0 to 9. With these, we can make all the numbers that we want because we use positional value. We have positional value and we have 0 and we have positional value. In order to have true positional value, you need to have a base. Our base is base 10, and you need to have 0 and 1 for counting number less than the base. You know, people don't realize the importance of these two numbers, 0 and 1. That's the whole foundation of the binary system. And the most common positional system, base 10, that we use is called also decimal number system. Hindu Arabic numeration requires fewer symbols to present number as opposed to other numeration system. As I said, these digits, 0 to 9, from them we can build all kind of numbers. And they have unique names from 1 to 12, then 13 through 19, they are called teens, and so on. And for numbers from 20 to 199, the 10th place is named first, followed by the number. Okay? Numbers from 100 to 999 are a combination of hundreds and previous names. So we have, these are clear, For example, 5630 is called 56,000. 5083 is called 5083 because the position of 8 is in the 10th position. Following me? Okay, clear?
Yes.
Okay. Now, we come to exponent and exponential notation. If n is a natural number, and again, natural number 1, 2, 3, 4, and so on, b to power of n means b b appears as a factor of n times. What I mean is 4 to power of 3 is equal to 4 times 4 times 4. Okay. b to power of n is read the nth power of b, or b to power of n. The nth power of b is defined as a product of the factor of b. This is called exponential expression. b to power of 1 is equal to b. b to power of 0, any number to power of 0 is equal to 1. Okay?
Good to know.
Now, let's look at example 1, checkpoint 1, page 195. Let me stop the share because I may have to block. Look at example 1 at the top of page 195. 10 to the power of 2 is 10 times 10. 10 to the power of 3, 10 times 10 times 10, and so on. 10 to the power of 4. 7 to the power of 1 is 7. 1 to the power of 7 means you multiply 1 7 times by itself. 2 to the power of 6 means that you multiply 2 6 times and get 6. Now, something very important is being able to have positional value in your numerical system. as you can see in the PowerPoint. The positional value in Arabic Hindu system are, it starts from, the very, depending how you look at it, I guess would be the left side, 1, 10, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5. It means we multiply to evaluate a numeral in the Hindu Arabic system. We multiply the first digit on the right by 1. We multiply the second digit by the base 10. We multiply the third digit by the 10 to the power of 2. Do you notice the third digit, let's call that n. In order to know what you need to multiply that, if it's a third digit and we are using base 10, so you take 3 minus 1, you multiply by 2, 10 to the power of 2. Are you following? No. Okay, let me write it. This is one thing that has to be written. Okay. No, that's okay. Yeah. As you can see in the PowerPoint, it says we multiply. Says the positional value in the Arabic system, you start from farther right, multiply by 1. The second number, you multiply by 10 if you're using base 10. If I have 2 digits, the first one is multiplied by 1. The second digit, this is the second digit, going from the right, okay? Yes. Watch it, and you're on base 10. So 10 to the power of what? Take this position, it's a second position, n minus 1. It's a second position, 2 minus 1 equal to 1. This is what position? Third position. So the base is 10. What should I multiply? The number, it's the position is third, minus 1. So this is the 100th position. This is the 10th position. This is the basic unit position. That's why we say 134.
Right. Okay. Good.
Okay. 134 means I take you see this you have 1 time. Let's look at this example. You have 1 times 10 to the power of 2. You get 100.
And then
this 3 is 3 times 10 to the power of 1. You get 30. 4
times 1.
4 times 1
equals 4.
So you add this together, you get 100.
44. And so on with other numbers. Okay.
That's the proper positional system. Our system has an excellent positional ability to use. Those other numerical systems don't have that. That's why it's so difficult to use them. And it goes on. The fourth digit you multiply by 1,000. Okay. So basically, this is what I just said.
Okay.
You take the digit from the right, multiply by 10 to the power of n minus 1. If it's on a third position, 10 to the power of 2. Fourth position, 10 to the power of 3. Second position, 10 to the power of 1. Okay. We multiply digit place from the right. Therefore, we multiply the 8th digit multiplied by 10 to the power of 7. Using place value rule, we can write a number in expanded form. Now, here is the expanded form. We have 1,234. So look at it. It starts, number 1 is in what position? The 4th position. So it's 1 time, the base is 10. 10 to the power of? Why? Because 4, take the position, subtract 1. Yeah. 2 is in what position? 3rd. So 2 times 10 to the power of 2. So you get the 3rd position. The position of that digit, subtract 1, you find out what, and we are using base 10, so multiply by. It's, that's why you say 1,234. Okay? All right. Good. The Babylonian enumeration system is headache. They use base 60 and hexadecimal system. They don't have a true place value system, no symbol for 0, which leads to lots of confusion and ambiguity. Now, these things you got to be given to you. Otherwise, there's no way we can do anything. This is a positional value in the Babylonian system. 1, the 2nd digits multiplied by 60, the 3rd digit is multiplied by 60 to the power of 2, and so on. Okay. Well, for example, let's look at example 4. And let me see, are we on? Okay, yeah. Okay. Let's go to example number
4 in page 197. 100.
No, actually, I can just look at the text. In order to do example number 4, you need to have that table 4.1. Otherwise, there's nothing you can do. And you also need to have that positional value that you see at the top in those gray boxes, that you see that? 1, 60 to the power 1, 60 to the power 2, 60 to the power 3. Yes. Now, it says, if you have this example number 4, number 8, you have these symbols. You have two symbol looks like a V, and you have a arrow, moving, yes, and then 2 arrows, and 2 V's, yeah? Okay, that's our number. The Babylonian system. We want to find it in our Hindu-Arabic numeral system. And remember, the base, this thing, very important. 60. 60 to the power 1, 60, actually 1, then 60 to the power 1, 60 to the power 2, and 60 to the power 3. Okay? Yeah. Now, look at it. This here. What is it its place?
to the position.
This is one digit.
1, 2. Oh, okay. So that's the third position.
Third position. So, this. Okay. So, and based on table 4.1, those little v represent what?
1.
1. So I have 1 plus 1, then what? Multiplied by the positional value.
Right.
What is its positional value? It's in a third position. So remember, then minus 1. Minus 1 becomes 2.
Right.
So which one do I have to use?
60 to the power of 2. Oh, a 1?
Yeah. This is
third.
No,
it's in the third position.
Yeah. I'm sorry. Yes. This is in the third. So it would be this one. Yeah. Right. So it would be times 60 to the power of 1. Okay.
2006.
No. This is on the third position. No. This is base 10. We can't use this. I'm sorry. I'm confusing TPS with the Arabic system. No. Sorry. Over here. Right. So this is 1. So when you have it, it's 1 plus 1. Now, our base is 60. This is in it. First, second, third.
Right.
First, second. First, second, third. Yeah. We come to this.
Yeah.
I'm still thinking. I have to multiply minus 1. So it's 1 plus 1 times 60 to the power. Okay.
Yes.
Okay. What is this arrow?
10.
And what is this one?
1.
Times. Okay. This is second position. So it's 60. So don't do n minus 1 for these other systems. That's only for Arabic systems.
That skills work.
All right. Now, what is this? These two.
10.
It's 10 plus 10 plus
1
plus 1 times. This is the first position.
Times 1.
Okay. Yeah. And then when you do the multiplication of that, you end up with the number 788. All that, this is equal to 7882 in our Arabic numeral system. But look at it. We can write this number easily here, but we have to have a whole row.
Yeah.
Okay. All right. We can go to share a screen. Okay. So we talked about that. Let's go on. Then, oh no, crazier than that is the Mayan numeration system. And you have, you need to have that table in order to do any kind of operation. Otherwise, there's nothing you can do. Here, please don't get confused. I have approximated the numbers. So if you have, start with column A, okay? We have at the top, we have that 2 dots and 2 lines under it, okay? If we go back, what's that number? Is 12. You see that? Okay. So we go, so you multiply it by 12, okay? Or just look at what I'm multiplying. Don't think of anything else. Okay. Now the only dot is 1. Okay. You see that? So I'll multiply by 1. When you have that shape look like a football, is 0. Okay. The almost equal sign is, if you go back, is 10. All right. So we get what numbers we want to multiply. But where do I get those 8,420 and 1? You got to go to page 198. If you look at page 198, you have table 4.2, you have Mayan numerals, and there you have the place value on. So if you have that kind of a number, you have, the first number, what's its position? In column A at the top.
Oh, the third?
Yeah.
It will be the third position?
It's actually, why do you say third? You're doing that in your mind. Right. You're subtracting 1 from it. Look at it.
Oh, 4. Oh, yeah.
It's so a fourth position. Okay. Yes. Okay. Now look at the place value in the Mayan system at the bottom of page 198. You have 1, 20, and then 18 times 20. The fourth position is 18 times 20 to power of 2, which becomes 7,200. I rounded up to 8,000. So maybe I should have rounded up to 7,000 actually. Now, that dot, it's in a third position. So you have to multiply it by 18 times 20, 360, or I rounded up to 400. That little strange curvature, oval shape, it's in a second position, so we multiply it by 20. And the last number is in the first position, we multiply it by 1. I mean, its positional value is 1. Those blue colors tells you about the positional value, and the black ones are actually the Mayan equivalent numeral value, equivalent to our Arabic system. Do you understand this? Okay. I wanted to make sure. Okay. Let's continue. Oh, we already talked about that. Now, then we have Greek numeration system. Again, they're very difficult based on Greek alphabet. Each has a symbol, value, number, and a name. Alpha, beta, gamma, all the game. Roman numeral, oh man, it's huge. For example, Roman numeral for 154 is equivalent when you go there to that table. You see, you find 100. Where is 100? Is right there, C at the bottom.
Oh, yes, I see.
See that?
Yeah.
So was it 154? Yes. So 50 is right.
Oh, yeah, I see it. It's in the bottom.
Yeah, it's L. And 4 is right here, IV. So CLIV. CLIV, okay. The number 1,492, you can, 1,492, you can do it yourself. 1,000, just becomes, okay, yeah, it's right here. This is one, well, this is 1,000, 999. Maybe it is MCCCL. You have to find those value number from this table and add them up. You have to find in a way that adds up to that Arabic numeral number. MC, where is it? MCCC. Okay, yeah. You see, this is 353. CCCCL111. You take that and add it to this one. So you put it all next to each other and adds up to 100. What was it? 1,492. 3,495 is this. I'm not going to even try it to find again. Hebrew numeration system, again, based on Hebrew alphabet. They assign numbers to it. The Hebrew numeral don't have a base. They don't have a positional numeral system like the Roman numeral system. But for example, number 764 in Hebrew is that Hebrew value that you see. In order to calculate, you find value of 4, value of 60, and value of 30, and value of 40 from Hebrew, from this table. And then just add them together, you get 764. All right. Number base position. Let me make this bigger. Any counting greater than 1 may be used as a base for a positional value of numeration system. Positional value system has a base. So we have base 1, b to power of 0, b to power of 1, and so on. Position value, for example, if you have base 8, if our base instead of 10 was 8, well, starts with the positional value of the first further right digit would be 1, then would be 8, 8 to power of 2, 8 to power of 3. And again, here you can see it does apply that rule of n minus 1. Because we are, the only thing we have changed the base. Instead of base 10, we are using base 8. But we are using Arabic numeral system, so that rule of n minus 1 applies. Following me?
Yes.
All right. If base 2, the same thing. So computers, most electronic devices use binary system, base 2, or the octal, base 8, or hexadecimal, base 16. Right? Converting bases less than 10, for example, if we want to convert the number 453, but this is not base 10, so it's not R453, it's base 6. So we take, you see, 4, 5, and 3. We multiply 4, but because we are using Arabic numeral system, we can use the rule n minus 1. So 4 is in what position? So it multiplied by what's our base? 6.
Oh, 6. Sorry.
Okay. So we multiply 4 times 6 to power of what? 2. Yeah. You apply that rule n minus 1. Okay. Because we are in Arabic system or Arabic Hindu system. 5 is in what position?
Second.
So 5 times the base is 6, but still we are in Arabic system. So 6 to power of second position minus 1 is 1, and 3 would be is in first position, so it's 3 times 1. All right. Okay. So that 453 in base 6 is equivalent to 177 in our base 10.
But why does kind of reduce it?
Because the base is actually reduced. We are using base 10. It's not base 10.
I see.
Okay.
Okay. Wow, I understand. Basic.
All right. Or you can converting bases less than 10, again, same thing. Here we have base 8. Again, here, or keep in mind, our base is 8. So we take the digits, 3,615. We take the digit 3, digit 6, digit 1, digit 5. The base is 8, so they are all multiplied by 8. But we apply the rule of n minus 1. The digit 3 is in the 4th position, so it would be 8 to the power of 3. 6 is in the 3rd position, so it would be 8 to the power of 2. 1 is in a 2nd position, so it's 8 to the power of 1. 5 is in a 1 position, so 1 minus 1 is 0, so 8 to the power of 0 is 1. Actually, something I just not bothering me. You know, that thing is not correct. This here, the example 453. Can you tell me my mistake here? 3 is in what position?
The first.
So you, oh, actually, no, I'm sorry. I get confused. Yeah. So it's the 1st position. So it's n minus 1, 0. So 6 to the power of 0 is 1. Yeah, forget. Are you following me?
Yes.
Okay. So you do the multiplication and addition. The number 3,615 in base 8 is equivalent to 1,933 in our base. All right? And I think it's the same thing. I'm not going to, if base 2, again, you have that number 100,000, 101, 101 base 2. So you just take the digit, and the base is 2, just find the position, like the farthest one is in position 6, so multiply 2 to the power of 6 minus 1, 5, 2 to the power of 4, 3, 2, 1, So it's interesting. Such a huge number, you look at it, looks like 100,000 in our system. Actually, it's equivalent to 45 in base 2. All right. I think, let me see whether these are necessary. 204, 206.
So they're
Yeah.
greater than 10. Is there any difference?
No, same thing. Base 10, if you want to do the otherwise, you just make the division when you do, if you're doing the, going from base 10 to base 8, for example. Instead of multiplication, you do the division. That's the only difference. Okay?
And then here they are using letters.
Yeah. But okay, but they have to tell you what those letters stand by. Otherwise, there's nothing we can do.
Wow.
Okay. Check the page 208. Yeah, same thing. These are. We already done that.
Oh, I think I was in the wrong page.
Okay, actually, we are done. Who is that? Is there somebody at the door?
I don't know. I can do it.
All right.
204. Oh, okay.
Okay, we are done. Okay, Any question do you have?
No, I don't.
All right. Just remember, next week, Monday is a holiday, so we don't have a on-campus class, but please follow online. We can't cancel the whole week because otherwise we come short 1 week.
Okay. And it's a lot of material to cover. So
Yeah.
I'll be doing it too.
All right. Well, good luck, everybody. Pray for you. I mean, not good luck. God blessing upon all of you. If there's any question, please email me. I'd be more than glad to answer. So you're okay?
Yeah.
Okay. Let's finish with a prayer. Father God, we thank you for this session. And I do pray that you help all the students to absorb and understand these concepts that we learned and studied tonight. And bless them in their studying this course or any other class. In Jesus' mighty name we pray. Amen.
Amen.
I'm going to stop this. And I'm going to stop share and stop the video and meeting.